for example, G is a real algebra, we want to find the commutant.
Oh, I'm sorry, I probably should mention that I'm from the.
And the first one is if G is GLN. And the second is G L is the full prime. Okay, so this is the problem. Let me just explain this one. I will try to find things in two processes. First, I will explain this
Я
one.
не прикрываю.
And then I will say, and by this too, you can get the answer for the first one. Yes, this as algebra. Okay.
Everybody are welcome to ask a lot of questions. Okay, that's.
I want to know this is just the definition of GLA. And
I'm sorry, what in your notation means plus eta?
yes, I will just explain. Sorry, maybe I should change my color. Change the color.
Okay. So these are the projections.
This is upper triangular, lower triangular, and diagonal matrix.
Yeah.
Yes, and this bracket means the linear span of this thing. And you can say this just definition. Okay, so first, I'll say this element is not here. So why is it true? Because we can say if it is here, the dimension of this space is n minus 1. And if this is here, and you will see the dimension of this space is n. So this is not here. What I want to claim is that you have a utility and you add this element to here. And then I call this element.
What is this letter? Eta?
Maybe
okay.
You question about this?
Yes. Usually it's denoted like H, maybe because it's Cartan subalgebra.
Maybe
But-
H, yeah.
But I'm just wondering. Okay, yeah.
Okay. I'll try to explain this. And you just first you choose I equal to 1 and and you add all the bases, original bases here, and finally you will get minus EN. And then you add this element to here, and finally you will get 2E1 plus and 2E minus 1 and minus 1. So there is something, something is eliminated here. Then you just keep doing this process. Finally, you will get some, maybe some constant times E11. And then you throw E11 is here. And then you just repeat this process, you can prove all things are here.
Yeah.
And this is dimension n, and this is dimension n-1, so you can prove that these two linear spaces are isomorphic. And
Yes.
it's just proof that.
So these are all diagonal matrices.
Yes, yes, yes.
It's exactly different. So H with tilde is exactly what's called Cartan subalgebra for GLN.
Yes.
And well, just for future, but so these are exactly elements for which we considered eigenvalues, and eigenvalues were called weights, right? And for
And then
H, it was
GLN.
SLN weight, and this is GLN weight. Yes.
Right.
Right.
And we, all the things we do just add this element to this.
Mm-hmm.
And I should also explain these since such elements have no influence in the commutator. Since the commutator of this element with any other element will be 0.
It's in the center
Yes, yes. It's
of
in the
GLN.
center. So this just proves this thing. Exactly. Since from SLN to GLN, we just add some things which have no influence on the commutator. So the commutant should be equal. Yes.
Right. And another words, right? You have GLN. I'm just saying in other words what was said there. GLN is SLN, right? Plus scalar matrices. Or C, if you wish, right? Ci. Then, if you consider GLN with GLN, right? This is linear in every component, right? So this is SLN plus Ci, SLN plus Ci, right? Well, since it's linear, it's just commutant of this and this, of this and this, which is 0 because scalar matrix is commutative with everything. This is also 0 and this is also 0, so it's, well, the only thing which is left is commutant of this and this. Okay, thank you.
And for we know for any we have in dynamic we have this, and this is just the commutator.
Mm-hmm.
0, and this just means the very overview.
Yes.
So then I will try to prove that.
This is true for any Lie
Yeah,
algebra because it's a Lie algebra. Right.
And we should prove the inverse. What the inverse means is that we can represent, it's sufficient to prove that basis of SLN can be represented as a Lie bracket of
Or something from a solvent.
Something from SLN, then we finish the proof.
Yes.
And for we have these, and these is in SLN, this is in SLN. And these is, if J equals to I plus 1, it will be the basis of some basis of SLN. And also have we have these, and this is also the basis in SLN. So now we find the expression of basis in SLN with respect to some commute.
Right.
And then we prove the first one. Right.
Mm-hmm.
Just prove the
Yes.
inverse.
Now for B of
The
F.
second one, G is B of F. And F is a full flag. First, we do process since the definition of full flag. This is the definition of the full flag. First, we fix the basis for B. First, we fix the basis for B such that B. This can be done by some knowledge from linear algebra. And then it also definition of BF. BF is this one.
Yes.
And when we fix this basis, if you just look at this I from, for example, from 0, and then you can know that BF, the matrix in this basis will be the upper triangular mass matrix in this basis. So maybe we can write it like this. This is just the same notation we used for the previous problem. And you can note this commutative relation. This is very simple.
Yeah, that's what we're using all the time, right?
Yes, yes. And so then we discuss what happened in BF, since we know BF is all upper triangle matrix, and this gives some relation between I, J, K, L, and then we know what we will get by the commutative. And in B, we have, since this is upper triangular matrix, we have this relation, and then we have two keys, case 1. We could just consider order of this IJKL when we satisfy this relation. And then there are two keys. Actually, they are the same. And we just discussed if J equal to K, J equal to K means this is 1. And if I equal to L, we just get nothing, since the right hand side was 0. So we have to consider I less than thing. Then EIL is in G just BF. And
so what is our goal?
our goal is just analyze what basis go, and then just the span of the right hand side will be the answer.
Okay.
And so for the case 1 we have this. And for the case 2, well, you experience the same process, we will also have the same result. So this is the final. This is a strictly upper triangle symmetry.
Yes. Or in our notation of previous lectures, n of f, right? So b with b is n of f.
Yes, yes.
And actually you can do this kind of in the same way you did number 1. Yes. Yeah, thank you very much.
First part it was to prove. Number 2. In the first part it was to prove that b of f is not nilpotent. And I thought about it like maybe we need to find a stabilizer. Like in our case, it would be a matrix. Yeah, we need to find a matrix.
Yes, something not zero that lives in every element of lowest entry series. Okay.
Yeah. So it will be matrix from B of F, obviously, such that also exists some J. Algebra and such that GA will be equal to SA. And from that, if we will find G and A, we can say that so A lays in every D, E, I, J.
Yes, okay.
So, and that means that it's not important. So the only problem to find G and A. And I just consider basis J of SLN and minus AJJ is basis.
Right.
Where is I don't know. Do I need to remind what is this matrices?
Yeah, these are matrices with 1 on ith and jth place and 0 everywhere else.
Yeah, something like it's everywhere 0 and only in place ij it's 1. So and A, I choose A as 1 second, E1, 2, and G small as E1, 1 plus E1, 2. Also, we need to mention that E1, 1, E1, 2 it will be equals to E1, 2, and another thing will be just 0. It's everything is 0. So we can just calculate commutated. So GA will be GA minus BJ. And if we will calculate using this property, not property, just direct calculation. So we will get that it's equal to E1, 2, so just A. So here we are done. So we found J and A such that it's correct.
Okay. But what's important that G actually leaves, it contains a diagonal element, right? So it's not in n of f. So we actually use that B of f it's not strictly upper triangle, but like actually upper triangle. No, everything is okay. Just yeah.
Okay.
Yeah. No, everything is good. Yeah,
Okay.
just my comment.
And about
So
To be nilpotent,
Because in this case, B of F is our G algebra, right? Our Lie algebra, right? Ah, okay.
Right.
Yeah,
Okay, any comments, questions? I think it's proved. So this is for for full flag, right?
The second part. Yeah, first part for full flag and second for partial flag.
For partial flag, you actually would like to prove that it's not even solvable.
Yeah. And I wanted to use not the same technique, but maybe similar.
Mm-hmm.
Find a space. Like we have our D, I, J, and like we need to find a space that will be
inside every element of the direct series, right?
Yeah, but
Can you imagine what is? So first of all, you have partial flag. Can you remind what it means? Okay. Okay, so this is just a flag. Okay, partial flag. I mean, properly partial. It means that. What condition do we need on dimension?
On dimension that dimension I will be inside or less dimension bi plus 1 plus 1.
No, I think this condition. Sorry. This is not the correct condition.
Yeah, but
This is not the correct condition. Condition is
Yeah, maybe plus one. Maybe it was my type. I think plus one should go to the other side.
Yes.
So the idea, Christina, the idea is that you have they are all one inside each other, right? And for full flag, the step in dimension is 1. But for partial flag, what I call partial in this problem, it can be bigger than 1. Actually, I would like there exists some step, for example, some step, for example, from V2 to V3, where dimension jumps by more than 1. So actually, this.
Like there is, it's like B1 is dimension 2 and B2 is dimension 4 or 5.
Yes.
Yeah, I think no, my first idea was to find that space that will be stable with that.
Okay.
If I will change, if I will go down index, it will be stable.
It seems to me that a more direct way is just to find a dimension 2 example, where in dimension 2, just to find an example of 2 vectors in the algebra that can produce an infinite, the commutators of which can produce an infinite series of non-zero elements.
Which is
Actually, it's like
when
if
you
you
have
find the subalgebra, it's not solvable, and we just say
Yes.
that the whole algebra is not
Yes.
solvable.
So we would like to maybe find some not solvable subalgebra.
And
Like
in the
it's very
previous,
Ideal, I would
yeah,
say,
and
even
in the
ideal.
previous
in that extra subspace that when you do the big step, you can put a copy of SLN or SLK something.
Yes. Okay, maybe you can write something.
I think you understand more now.
Yeah, thank you, Christina, very much.
Actually, they need the elements of the Cartan subalgebra and.
We're gonna choose a base.
Yeah, you can assume something. For example, this jump happens on the first, from V0 to V1.
Okay. Yeah, I have something else. Okay, we can choose okay, again. We choose a basis, and we want to see how looks our elements of our algebra. So, if we have a jump of at least dimension 2, now I'm gonna like this, and for example,
Say it. Yes, okay.
So our elements in BF.
Right. You can even draw a matrix how it looks
Yeah,
like. Yes.
Actually, I can put like a small block. You can put there are this this you can put a copy of SL it's like in this.
Maybe even GL, right?
GL.
You're not restricted to zero, zero trace zero matrices, right? So even GLK.
Yeah. But at least it's this, and this is
right.
Not nilpotent, not nilpotent, so we can put it here. And for example, here we have our HA.
You just need one element which is below the main diagonal to produce such a sequence.
Yeah, I want to be formal, but I just have this idea. Okay.
Okay, let us not. I mean, you said everything right, yes. So.
Just okay, we choose that, and we can just choose. It should be 1 and 2, and 1, 2, and these are the basis of a copy of SL2. So when we make the commutant of BF, we can consider it like a big matrix with
this
some
block.
of these blocks in that entrance.
Right.
And in the rest, wherever we want. Of course, it has to be upper triangle or with something about these blocks, these kind of blocks. And when we make the commutant, we will get the algebra, this algebra. So it's not nilpotent. So this will be non-zero. Like each time we do
right.
again commutant.
Right.
That's the idea.
Yes. Yes. Okay. Yeah.
I think I have another idea about but my idea is just work for proof it is not nilpotent.
Sure.
We can just and consider V common some common sense from some common sense and consider the projection or
V quotient. What stands here?
it's like I won't get a full flag because like if the dimension here is maybe 0 and this one is maybe 3 and
Right.
the something and there is a if it's 3 it can be 1 plus maybe u and the u is something 2-dimensional and we caution 1-dimensional from here.
Okay.
And
Then you have to quotient in every other.
every step, and we get some maximal things we need to quotient, and then we get a full plate.
Okay.
So the algebra acts on this thing is equal to. It's not equal, but we get some another action to a full plate, and then use the first.
But what are you trying to prove though? That it is solvable?
Yeah, no, the problem is the proof it's a nilpotent.
The proposal is not solvable, but non-nilpotent is not enough. Because non-nilpotent may be solvable.
Yes, yes.
And George, a way to prove this and exactly.
Okay.
Suppose your flag is not full, and so your algebra contains at least one. So you have these matrices, and there is at least one element in this algebra that lives below the main diagonal. So we can use the direct notation. And there is also the corresponding element symmetric, which lives above the diagonal.
Okay.
And in direct notation, these are, we can denote them, for example, B, A, and A, B.
That's cool, yeah.
Well, and basically, all we need to produce an infinite sequence of non-zero commutators.
So your notation corresponds
So
to our
these are projectors.
like this, right? This is EBA
Yeah.
and this is EAB. Okay.
Yeah, and so
We have some physicists in the room.
yeah, we can observe that if we take the commutator of BA and AB, we get A, B, B, A minus B, A, B,
Right.
and these are just some coefficients. And so this commutator produces.
These coefficients are 1 actually.
If we take yeah, okay.
Yeah.
If we take the basis in which
Yeah. If we consider
Yeah.
this identification, it's 1. Yeah. Of course you can take.
Identification is just one.
Yeah.
So we have this element of the Cartan subalgebra. And now we need the element A, for example, A, and acting on this element with our commutator in a joint representation. We can use the same physical notation. Well, so we have A comma A minus, or not comma, but B, A outer A minus B outer B. And this we commute with A.
Again, so can you announce what is your goal?
Yeah.
What you're trying to prove?
Just I was going to say, I was going to just skip all the computations.
No, commutations you need for for something, right? So
yeah, and just tell that in the end we have 2A comma outer B minus the thing we began with A minus B. So we acted on it with this commutator.
okay.
And produce something that contains the commutator itself. and this thing.
Okay.
And so we can use this element again to put it in another commutator with a outer A and continue. So we can just put this in a commutator with a outer A and continue like this forever. Each time we will obtain at some point with this thing, which will act non-trivially in the adjoint representation on this thing. And so the sequence of commutators will never terminate in zero. First we need to show that a nilpotent algebra of dimension 2 is abelian.
Right.
Which is kind of obvious because we have just proven that, in fact, we've proven a version of Engel's theorem that in a nilpotent algebra, all elements must be nilpotent themselves.
Like
In adjoint.
image of adjoint element is nilpotent in the sense of operators. Yes. Okay.
And so basically, what that means is that if you have an abelian algebra, its elements can be represented as upper triangle.
So you start with nilpotent, not abelian.
Yeah.
So you start with nilpotent and would like to prove that it's abelian.
Yeah. But it can be done the other way around. Like if we have if we have an nilpotent matrix. Wait.
You can also start like supposing that it's not abelian.
Yeah,
Yes.
since it's nilpotent, there is a basis
Right.
in which all its elements are strictly upper diagonal matrices, and in the case of dimension 2, that means just matrices like this, which commute.
I agree. So you're using Engel's theorem.
Yeah.
Okay.
And the second
Apply to adjoint representation. Okay. So you have a basis in which all your images of adjoint representation look like this. I agree. So.
To the second part.
Okay. Sorry. You need to prove that nilpotent is abelian.
Yeah, but
I think I didn't catch
these
it.
matrices compute, don't they?
They do. Yes, that's true. But you have. It means that adjoint, like. So what you proved is that. So suppose that G is your nilpotent two-dimensional, right? And you prove that add of G is abelian.
Yeah.
So how do you prove that G is abelian?
I think there is a theorem that isn't adjoint representation always exact, or
No, not.
oh.
You have idea how to argue that?
No. I'm not following his.
No, maybe we can, finish this and then your idea. It's not true that adjoint representation has no kernel. So you agree that you proved this one.
Yeah.
But how from here you would like to prove that G is abelian?
And we wrote G like this.
Oh.
So, then I suppose the D algebra Lie bracket will be like this. Okay.
So you're basically proving the second part of the
No,
problem.
this
and
is
from this you-
the structure constant structure of the Lie bracket.
Right.
Structure constant. Yes. And we just set like this, and we look what happened here. And this will be this, right? Let me expect such a
Mm-hmm.
okay. And and we compute this. This is very trivial. This is just b times a plus b1. And also we can compute these.
Mm-hmm. Mm-hmm. So you're first proving the second part, and then you would like to prove the first one.
Just compose the joint representation.
Yeah.
Okay.
I say here, if neither a or b nor b is not equal to 0,
Right.
it will be not be nilpotent. Since you just what we are doing here, we just doing this. We just take this. If neither a or b is not equal to 0, it will also be safe. It will be stable.
Yeah. If it's not 0, then this equals to again to GG, right?
Yes.
But we don't want this because
Yes,
then
yes.
then it stabilizes not on 0.
So yes. So with loss of generality, we just suppose a is equal to 0.
And this is the proof already of the first one, right?
Yes. And if you suppose a equal to 0, and you just repeat the claim that this non-nilpotent, it will be that b is equal to 0. So you get ab equal to 0, since this equal to 0.
Right.
So, I mean,
Right.
And we have a second part.
Yes. The second part you can continue out of
Yeah,
this.
that's actually how I
relation.
did this.
Yes.
So basically, I just wrote out this commutator, and then
Mhm.
I do a change of basis, which is non-degenerate. So I just have a matrix alpha, beta, gamma, delta,
Mhm.
such that alpha delta minus beta gamma does not equal 0. And compute.
Sorry, what is this matrix again?
It's the matrix with which we act on the basis x. We change the basis.
okay,
And
okay.
what we want
Yes.
is after the change to obtain a new bracket in
Yes.
which only x is present
Mhm.
as a result.
Yeah. But all right, you don't need even this matrix, right?
Okay, so
It's kind of straightforward, but it can be seen like from here already, right? You almost got this the vector such that x with this vector is this vector itself, right? Already, you just need to rescale it. So you either a or b is not 0, right? So suppose b is not 0 and you have this, right? So you take z, right? To be what? So okay, if my z is ax plus by, right? Then x with z is bz. So how should I rescale z? So I would like z tilde, right? Such that x with z tilde is z tilde. Right? So how can I rescale? So z tilde is something times z. Right? My claim is that we don't need like the whole matrix, maybe just to rescale this vector somehow.
I'm not sure, but
Yeah, so maybe let's take, so let me erase this. Well, maybe you can say right away what should be C.
I didn't miscarry the just one. I just going to.
Write some equations.
Write some-
see,
It's solvable.
in fact, for me, it was.
So you used
like-
matrix, right? Or something like more
okay,
general.
in my solution.
Okay, so
what I got-
maybe let
Yeah.
let me not mess up your solution. So
what
let's
I got is
just
that
continue.
the matrix it's sufficient to demand the matrix to have the determinant equal 1,
Yes.
and after that we get like so if x y equals k1 x plus k2 y, we have k1 equals alpha divided by alpha delta minus beta gamma, and k2 equals beta divided by the same determinant. And if we demand this determinant to equal 1, we get just k1 equal alpha and k2 equal beta, and then we search for the two coefficients that are left free. And we can just solve the equations, the two equations for the two coefficients that are left undetermined.
Okay. Is it linear equation?
We can okay. We can just yeah. I think it's it should be linear because here we demand this to just equal 1, and so we obtain k2 equals b and k1 equals alpha. And then we have the two elements of this matrix plus the condition that the determinant equals 1. And so basically we solve what's left.
Okay. So so here you prove that you can do here actually. So here is explicit almost.
Since we know that ax plus by is invariant, and we just one of the things is suppose a is not equal to 0. Since one of ab is not equal to 0, and you can check that the Lie bracket of v and w is b. So we got a new basis, b, w. Lie bracket of v and w is b. And will be like this.
It's just so I guess you got it like.
Yes, but first
So how did you get this
I
formula?
tried to do these things,
Okay.
but there is still some problem with the scale.
You're
So, since a is not 0, I just divide all things by a, and I know these things. And so I know these things, and then from public is very easy to do.
Okay. Yeah. So here's my solution. Again, what I was saying is almost true. I am not rescaling z though, but rescaling x. So again, from what I would like to start from here, right? It's either b not 0 or a not 0, right? So suppose I have not abelian, right? Not abelian algebra of dimension 2. So it means that either b or a is not 0. So suppose b is not 0. Then, as I wrote, if I denote z to be ax plus by, right? Then x z is b z, right? But then instead of x, so I was trying to rescale z, which is not a good way. Instead of x, I take x tilde, which is x divided by b. So here b is not 0. And then I have then my g is actually has basis x tilde z, and from here it's obvious that x tilde commutator with z is z.
So it's 1.3 and no.
Mm-hmm.
And it's proof that non-abelian
Of dimension 3, yes.
isomorphic to Heisenberg.
Mm-hmm.
That it's generated by where the rules of commutation they are the following. And the rest. Okay.
Mm-hmm.
So, first, okay, we have that this Lie algebra is of dimension 3.
Right.
So we can say that it's generated by x, y, and z. And okay, so we're gonna take the commutant. But because this is
So you take any basis, right? So
yeah,
okay, and then mm-hmm. Mm-hmm.
And because it's nilpotent, the
Right.
dimension of this one has to get lower, like
Right.
at least by 1 or by 2,
Uh-huh.
but not 0, cannot be 0 because if it's 0, it would be abelian.
I agree.
So it
Yes.
can only be 2 or 1.
Mm-hmm.
So if it's 2, the dimension of this is equal to 2. This is the first case.
Okay.
Then we will take that. We can choose 2 of these ones
Right.
and say that it's generated by these ones.
Okay.
And so this is again nilpotent, please.
Right, because it's an ideal inside nilpotent, right?
Yeah.
Mhm.
This is nilpotent, and it's of dimension 2.
Right. But we proved,
And we just proved in the
That it's
previous,
abelian.
problem that it's abelian.
yes, very good.
So.
It means that commutator of xy is 0.
Yeah. This is 0.
But you can take z now, right?
Yeah. I'm gonna check how is the commutant with z.
Uh-huh.
With all this is here.
Mm-hmm.
So this is again this is generated by these 3.
Mm-hmm.
So we can write them here. And this commutes with itself.
Right.
And so this The same with the commutant x y. So, and this is this, because we got that.
Right, right. Mm-hmm.
So you can get and then if this is not zero, it shouldn't be nilpotent, because we can repeat and repeat and repeat, and it will be zero, and then it wouldn't be nilpotent.
Mm-hmm.
So this should be zero.
And you can write it like this because well, you can take like any element with something from xy, but since xy commute, right, the only way to get non-zero is with z, right? So therefore, an element from here is written like that. Yes.
Okay, so this cannot be. And then we're going to check the dimension. This is 1. Then we can say that the commutant is, we choose a base, in this case we can choose x, for example. And then we're going to check the commutant relations between them. So we have that y and z.
If you would like to match Heisenberg, it should be z, right?
Okay. Yeah, it's like this.
Z.
Z.
Yeah. Yeah, because each element here is generated by z, so
Mm-hmm.
this it's again here, so it has to look like this.
Right.
Okay, so and for x equals 0, we will have something like this, but there is a problem because okay, here we can rewrite as a commutation of xy. And
Right. So you would like b to be 0, actually, right?
Mhm. Yeah, it's supposed that it breaks the nilpotent again.
Mm-hmm. But x with z should belong should be 0 because
Because we have it's no abelian, right? If it's not zero, it's no abelian, and it's dimension 2 subalgebra, which is nilpotent. And in the previous
who is subalgebra? No.
xz.
xy. xz.
Yes, xz. If your b is not zero, then xz will spend two-dimensional subalgebra.
Right.
And
It's
nilpotent.
It's not
nilpotent.
it's not nilpotent. Then.
It's not nilpotent, but it's nilpotent since what g is nilpotent.
Right. But
So
if b is not 0, then it's not nilpotent, and it's a contradiction,
Yes, contradiction. Yes.
right?
That's what I want.
So again,
yeah, because we can repeat
Yeah.
it, and we will have again something with 0, right?
mhm. But it's also an ideal because so then x, something which is spent on x at z is an ideal because of this as well.
If this is different to 0, and then it wouldn't be. Then this is not we can repeat this and it would be.
Yeah, this is also an
And
argument
it's the same for.
for y and z. Yes, very nice.
For me was not clear. Okay, yeah, I did that also, but why it's zero? Commutator, commutator, commutator. Why it's zero?
This one,
No. That's.
This one.
Yeah, the Heisenberg.
so it should be zero. Otherwise, we repeat this, and it is repeat again and again, and your lower center series then will not stabilize at zero.
So maybe I should. Yeah, like from here, I should be right here. Because this is the generator of this. So you can rewrite this again. And if you can rewrite again theta? No, right?
Mm-hmm.
Because the commutator with itself. And what else? This will get. I forgot what was this.
So these are linear combinations, right? And actually, you have that x and y commute with x and y, right? And therefore,
Yes, you. I think we just analyze the dimension of this.
which one?
Just. Just you change this to g. You analyze the dimension of these things. If the dimension is zero, then it means it's not abelian.
If the dimension of is zero, then it's not abelian. Why? This can be zero, right?
Yeah, but this is zero means the abelian.
Right, right. So
Yes, because we use the previous things, there is no two-dimensional non-abelian nilpotent sum. So if it's equal to zero, then means it's not abelian.
So I'm a little bit lost. So here we are proving that dimension of this cannot be 2, right? And again, so how?
So we calculate this as generator.
So suppose it's 2. Yes. Suppose you have x, y.
We already proved it.
We get d.
So where we did get stuck. So if we already proved this, then this is not
Actually,
two.
because this we can get the zero again here, right? Like directly. And because
Sorry, I am lost. Whether we have proved this.
No. We're trying to prove that this is not possible.
We're trying to prove this is not equal to 2.
Yes.
Okay,
Yes.
suppose this is equal to 2,
Right.
and you analyze the dimension of that thing.
Yeah, but how?
I mean, here we'll survive only x and z and y and z,
Right.
and then we will get again like 2 theta.
Right. Maybe linear combinations.
Yeah.
Right.
Yeah. Okay. Here, die because of 0, and extend this. Okay.
So maybe let me try to finish. Okay. So so here what it is meant, this is a linear combination of x, y, and z. All right. So this is you have z with something like a1x plus b1y plus c1z commutator with some other linear combination, which is a1x, a2x plus b2y plus c2z, right? And we proved that x and y commute, right? So the only thing which is left is z with x and y in here, right? And this z with this x and y, right? So these are linear combinations, actually. So we have z of, with some coefficients, right, of elements of this sort, z, with something, with some vi's, right? And then we actually
these vi's, they are only with x and y, right?
yes, but this is in the next element of the lower center series, and then we can continue. So this element lives in all elements of the derived series, so it should be 0, right? Since our algebra is nilpotent, right? At some point, lower center series becomes 0. So we proved that this element actually lives in all lower center series, because then we again repeat and get some linear combinations when I have 3 z's here, or 4 z's. At some point, I arrived at an element of lower center series which is 0.
Okay.
So it should be 0.
The problem is with the algebra, it's subalgebra in GL some V, and any element in this algebra is nilpotent. So then we need to prove. What?
That add x is nilpotent.
Ah, yes. So add x is so by the N-Gauss theorem, so if we have this condition, we know we can choose the basis to make every element in this algebra becomes upper triangle. Strictly upper triangle.
Upper triangle.
So we can always consider this guy is the subalgebra of upper triangle. This is the algebra. This upper triangle matrix is the algebra.
Yes.
Yes, and then what is at x is it's like if we choose anything at x, y is x y minus y x, and this thing is belongs to
Nilpotent means what? Can you remind?
This guy is nilpotent means that we have we can find
For some n, yes.
So if we add some this action to some another vector from this guy, and we get some element in this, and this is the
I agree.
in this. And if we add, if we do it again, like square, then we got something in. This become D2. And we do it again and again and again. This, but we know this guy is nilpotent.
Yes,
So
therefore at some point. Yes.
It means this guy in some position becomes zero.
I agree. Also, there is a proof without using Engel theorem. So actually, in Serre's book, this is statement is used to prove Engel's theorem, and you can see it directly as follows. There is no proof of Engel's theorem in Kirillov's book. So if you go to Serre's, which Kirillov recommends as to get all missing parts of his book, you go to Serre's. So actually you have add x is Lx minus Rx. Where these are linear operators in so what was our algebra? G, right? And this one is also in here. So what is this? This is multiplication from the left, right? So Lx acts on some element y as x, y. So these are actually the morphisms of G, so you can do this, right? And this is in GLV. Everything happens in GLV, so multiplication of matrices. And Rx acting on y is multiplication from the right, so it's yx. Then this formula is clear, right? So taking commutator is multiplication from the left minus multiplication from the right. Now Lx is nilpotent, right? Just because every element is nilpotent. If I take some power, so it just means I multiply from the left by some big power, right? So, and similarly, Rx is also nilpotent. So they are nilpotent. And they commute. Because multiplication from the left commutes with multiplication from the right. So as two operators, as two linear operators on G, they commute. It means that if I take Lx minus Rx to some big power, it will behave. So the formula is like a Newton binomial formula, since they commute, right? But in Newton binomial formula, so suppose that Lx to the power n is 0, right? They are nilpotent, and Rx whatever, it's also to the power n, but maybe it's another power. I don't even care. Then you can choose that from the Newton binomial formula that if I take this power, everything that is inside will contain powers of all L or R greater than N or M. And so this is like This is one of the steps in the proof of Engel's theorem in Sierra's book. It uses commutativity.